Written in the 2nd century CE, Claudius Ptolemy's Mathematicae Syntaxis, better known as the Almagest, became the most important text in mathematical astronomy for the next 1,500 years. But despite the historical significance of this text, it's nearly impossible to find detailed information on how its models were derived and functioned. So much so that when I began studying historical astronomy, I decided it was best to sit down and work through it myself. So in this series, I'll share what I've learned about one of the most important astronomical texts of all time. I'll begin by addressing things conceptually, so viewers that aren't interested in the detailed mathematical workings can get an appreciation for Ptolemy's work. With that out of the way, I'll then explore select mathematical topics, taking the understanding from the conceptual to functional, allowing viewers to understand how the models were practically applied. In this video, I'll be exploring Book 4. In this one, Ptolemy begins exploring the lunar model, developing his first version, believed to be based on the model of Hipparchus. So join me as we learn how Ptolemy defined astronomy before the telescope. Ptolemy begins Book 4 by asking the question of what sorts of observations will be needed to calibrate the lunar model. In Book 3, Ptolemy got away with determining the position of the Sun for calibrating his solar model by a trick of geometry. By definition, the Sun is a quarter of the way through its motion about the zodiac at each successive equinox and solstice, allowing its position to be precisely defined so long as the dates and times of those events could be determined. For the Moon, he will exploit another geometric necessity by making use of eclipses. When an eclipse occurs, either solar or lunar, we know that the Moon must either be directly in front of the Sun for a solar eclipse, or directly opposite the Sun for a lunar eclipse. Since we now know how to calculate the position of the Sun at any given time, that means that we will be able to precisely know the position of the Moon as well, at least insofar as the solar model is accurate. But there's a catch. The Moon is close enough that it exhibits significant parallax. This actually means that solar eclipses aren't good enough because our position on a spherical Earth can allow for a solar eclipse even when the Moon's center is not precisely aligned with the ecliptic. Thus, Ptolemy will only make use of total lunar eclipses, which play out independently of the observer's position on Earth. You may be concerned because the width of the Earth's shadow at the lunar distance is about 2.5 times the Moon's diameter, which means that it may be slightly above or below the ecliptic. But Ptolemy, as we'll see, is primarily concerned, for now, with the ecliptic longitude, which, at mid-eclipse, is pretty close to the straight line Ptolemy seeks. Ptolemy then goes on to give a brief description of how lunar eclipses work, noting that the Earth casts a cone-shaped shadow behind it, and that lunar eclipses are the Moon passing through this shadow. And while solar eclipses play out differently, depending on your location, lunar eclipses are identical to every one on Earth, with the exception of happening at different local times. Just like Ptolemy began Book 3 with a discussion of the period of the Sun, he now goes into what a period of the Moon means, and it's significantly more complicated. As Ptolemy tells us, the Moon's motion appears anomalistic both in longitude and latitude. The time it takes to traverse the ecliptic is not constant, and neither is the time that it takes to return to the same latitude. What Ptolemy is telling us here is that the Moon's motion is complicated. The Sun is, by definition, confined to the ecliptic, although it moves around it at a somewhat irregular rate, speeding up and slowing down as it goes around. But the Moon has its own circle that it appears to trace out in the sky, which is inclined to the ecliptic by about 5 degrees. This creates a bit of a problem since the ecliptic is our fundamental plane that we measure by. In general, the moon follows the ecliptic, but since its circle is slightly inclined, it will bounce up and down relative to the ecliptic. However, when the moon returns to the same point in longitude, it won't necessarily be at the same latitude that it started at. Its cycles are out of sync. So how do we deal with this? How can we even define a lunar period? The answer is that there isn't one answer. We'll need to consider and come up with average periods for all of the types of lunar periods that the moon can exhibit. Defining those periods and putting together a plan on determining them is the real focus of Chapter 2. Even if the time that it takes for the moon to return to the same ecliptic longitude isn't the same as the time it takes to return to the same ecliptic latitude, if you wait long enough, eventually you'll have a return in both latitude and longitude at the same time. It's kind of like watching the turn signals on two cars in front of you. They go out of sync and then come back together. Their periods are different, but after a while, they'll briefly line up again, before getting out of sync and then lining up again. Ptolemy states that the ancient astronomers, likely referring to the Babylonians, looked for cycles in the moon's behavior by looking for patterns in eclipses. And they seem to have found one with a period of 6,585 and a third days, just over 18 years. Today, we call this period the Saros cycle. In that period of time, the moon seems to go through an integer number of returns in latitude, anomaly, and lunar phases. Let's first consider the lunar phases that I just mentioned. In a Saros cycle, the moon goes through a full cycle of phases known as lunations 223 times. If you divide 6,585 and a third by 223, you would get the mean period for a lunation. This is known as a synodic month. Second, as we noted, the moon has anomalistic motion in which it speeds up and slows down. The amount by which it does so is fairly dramatic. Some days, the moon moves by about 10 degrees, but others, it moves as much as 14 degrees in a single day. For scale, the moon's angular diameter is about half a degree, which means that that difference of 4 degrees is about 8 times the width of the full moon. In 6,585 and a third days, the pattern of anomaly will occur 239 times. And again, if we divide 6,585 and a third by 239, we get the average period of anomaly. This is referred to as an anomalistic month. Third, if we track the moon bouncing up and down with respect to the ecliptic, we'll find that in a Saros cycle, it does so 242 times. And again, we can divide the Saros period by this to find the average duration of a return in latitude. This is called the Draconitic or Draconic month. Lastly, we can ask how long it takes for the moon to return to the same ecliptic longitude. However, the moon doesn't actually have an integer number of returns in ecliptic longitude in a Saros cycle. The reason should be pretty obvious if we think about it for just a minute. It's because the Saros cycle incorporates an integer number of lunar phases, which happen when the moon returns to the same position relative to the sun. However, since the Saros cycle isn't an integer number of years, the sun won't have returned to the same ecliptic longitude in that amount of time, and thus neither will have the moon. But Ptolemy still wants to determine an average period for the moon to complete a circuit about the ecliptic. Fortunately, we can still get there using the Saros cycle. We're just going to have to do a bit more work than dividing the Saros period by the number of returns. Instead, we need to notice that, in a Saros cycle, the sun has moved 10 2/3 degrees further than an integer number of 360-degree revolutions around the ecliptic. Since the Saros period returns the moon to the same position relative to the sun, the moon too has moved by that much extra. Ptolemy then notes that some people don't like the fact that the Saros cycle has that lingering third of a day in it. I guess fractions are hard or something. Fortunately, if you want to get rid of it, you can multiply the Saros period by 3 to get a related cycle, referred to as the exeligmos, which is 19,756 days long. I should note that I've been doing a bit of foreshadowing in this chapter. Although I've been describing how we could get an average period for each of the types of lunar months, Ptolemy holds off on the actual calculations until the next chapter. That's because the vaunted Saros cycle we've been discussing was already known to be wrong, thanks to Hipparchus. Instead, the period Hipparchus uses is 126,007 days and 1 hour. In this period, he finds 4,267 lunations, 4,573 returns in anomaly, and 4,612 returns in longitude, minus 7.5 degrees, again related to the sun's position being different. And because this cycle has a longer baseline, dividing the total period by the number of returns to figure out the average lengths of the various months should give an even more accurate determination for each of the types of lunar months. But if you're paying close attention, you may have noticed that I didn't give a number of returns in latitude for this Hipparchan cycle. Ptolemy calls this out as well, noting that this Hipparchan cycle didn't have an integer number of returns in latitude. It was very close, and the eclipses still repeat, but the size and type of the obscuration is slightly different, meaning that the pattern isn't perfect. This is frustrating because it means that we can't use this cycle to determine the length of a draconic month, at least not directly. Instead, Ptolemy cites Hipparchus again, stating that there were 5,458 lunations for every 5,923 returns in latitude. Thus, by knowing the synodic month accurately, we can use this ratio to determine the missing draconitic month. If you're feeling lost with all of this, Ptolemy certainly shared your pain and acknowledged the complexity, stating, "It is not simple or easy to carry out, but demands a great deal of extraordinary care." Finding a true cycle of eclipses is challenging because it's possible to get false positives where you may think that you found a cycle in which a few eclipses happen in a similar fashion in a similar amount of time. But this could just be a coincidence. He then goes on to describe the necessary conditions for establishing a true cycle of eclipses. Yet, despite all the careful consideration that Ptolemy tells us Hipparchus did, he still determines that there are issues with the periods of anomaly and latitude, so considerable as to become quite apparent to us. However, he doesn't address them here and promises corrections which we shall derive later. In Chapter 3, Ptolemy completes the calculations to determine the mean periods as we described previously. However, instead of expressing them as periods of return, he expresses them in degrees per day. And, as we did with the sun, we'll also be making a lunar mean motions table for convenient use later on. However, in addition to the mean motions in longitude, anomaly, and latitude, he also takes the difference between mean motions in lunar and solar longitudes. This will be used to determine how far away the moon is from the sun about the ecliptic, a property known as elongation. This is important in determining lunar phases for eclipses, which we'll be exploring in Book 5. The tables themselves are in Chapter 4 and broken into the 18-year periods, single-year periods, Egyptian months of 30 days each, single days, and hours, just as they were in the solar table of mean motions. However, due to the issues Ptolemy hinted at the end of Chapter 2, the values for the periods for anomaly and latitude don't actually correspond to what we would get if we performed the calculations based on the periods we just discussed. Rather, Ptolemy has sneakily used values based on corrections to the anomaly and latitude, which he has yet to discuss, and which we'll come back to in Chapter 7 for the anomaly, and Chapter 9 for the latitude. With these mean motion tables laid out, Ptolemy is ready to begin the real work on the lunar model. Again, asking which hypothesis should be used, the eccentric or epicyclic. And again, he concludes that it doesn't matter for the simple lunar model, which sure sounds like it implies a more complicated one. Spoiler, there is, but we'll come to that in due time. Ptolemy almost immediately lays out why we can use either lunar model for now. He states that the model we're about to develop is treated as if it only has one anomaly in longitude, and that this anomaly corresponds to the above period of return, which is the only one which our predecessors, just about all of them, have hit upon. But, as we'll see later, Ptolemy discovered a second anomaly linked to its distance from the Sun, i.e. the elongation. He tells us that this initial model works well when the Moon is precisely at conjunction and opposition, full or new phase, but has problems near the first and third quarter phases. It shouldn't be too surprising that this model works well for the full moon, since we're going to be building it using lunar eclipses, which happen at just this phase. Ultimately, Ptolemy settles on using the epicyclic hypothesis for this lunar model. To calibrate it, he begins by trying to figure out the size of the smaller circle, the epicycle, as a proportion of the larger circle, the deferent. As he did with the Sun, he doesn't try to determine the sizes in absolute terms. Instead, he again treats the deferent as a unit circle with a radius of 60 parts, and then gives the size of the epicycle, again in parts, in relation to this. Obviously, since both the Sun's eccentric circle and the Moon's deferent circle both have radiuses of 60 parts, the parts for each of these are different size parts. Confusing to have two different units with the same name, I agree, but this is quite common, and Ptolemy will be bringing them into a single system of measurement later on. But to determine the sizes of these circles, he uses a series of 3 eclipses, which I'll call A, B, and C, which came from the Babylonian records. He first determines the ecliptic longitude for each. This is done by calculating the position of the Sun for each of them using the solar model. Then he can add or subtract 180 degrees to the solar longitudes to determine the lunar longitudes, since the Moon must be opposite the Sun. Next, he pairs off the eclipses, A with B and then B with C, and asks how far the Moon moved between each pair. However, this total motion is apparent motion, which is comprised of both the mean motion, about the deferent, and the anomalistic motion, caused by the motion about the epicycle. Fortunately, we can determine how much of that motion was caused by the motion about the deferent by taking the interval of time between the members of each pair, and then using our lunar mean motion table. Then, whatever's left must have been caused by the epicycle. Essentially, what Ptolemy has done is subtracted out the mean motion from the deferent. This allows him to only consider the motion about the epicycle. Then he can sketch out the residual angles that were caused by the epicycle from the vantage point of Earth. At this point, we don't know if the Moon was on the near side or the far side of the epicycle for each eclipse, but doing this will cut off some arcs on the epicycle. Ptolemy is able to determine how long the arcs should be by taking the interval of time between the eclipses in each pair, and then determining how far about the epicycle the Moon should have moved from the mean motion table. From this, he determines that arc AB should be 306 degrees and 25 minutes, and arc BC should be 150 degrees and 26 minutes. Then, Ptolemy can ask how he must arrange the epicycle and the eclipses on it so that everything lines up. This reveals that the eclipses must have been arranged like this, with A and B on the far side and C on the near side. Then, through some geometry, he's able to determine the distance at which the epicycle needs to be positioned as well as its radius. To check himself, he repeats the same calculations using a series of 3 eclipses observed in his own time to show that the size of the epicycle, based on his contemporary observations, is in nearly perfect agreement with that found from the Babylonian eclipses. As I promised before, Ptolemy now discusses the correction that he did regarding the mean period of anomaly. Now that we have some hard numbers for the lunar motion instead of the somewhat fuzzy logic from before of, well, these periods all seem to line up after a Hipparchan cycle, Ptolemy has checked the values to ensure that they match with what's expected. The mean period for longitude seems good, but the mean period for anomaly is off by about 1/4 of a degree. Thus, when computing the mean motions for the table in Chapter 4, they have been computed with this minor adjustment already built in. Now that Ptolemy has gotten the base layout of the lunar model all set up, we'll again need to determine an epoch position from which to perform our calculations. This is done by picking one of the eclipses for which we just determined the lunar position. We can then use our tables of mean motion to rewind the motion about the epicycle and the deferent, and figure out the orientation at the beginning of the epoch. For that epoch date, Ptolemy uses the same as he did for the Sun, the first day of the reign of Nabonassar, the 26th of February, 747 BCE. Doing so, he finds that the moon's mean position was 11 degrees and 22 minutes into Taurus at that time, which was 70 degrees and 37 minutes from the mean position of the Sun. Then, for the position on the epicycle, he found that it was 268 degrees and 49 minutes from apogee. But notably absent from the list of values for the lunar epoch is where the moon was in ecliptic latitude at that time. And this is because he still needs to discuss the correction for the mean motion and latitude. He does so in the next chapter. There, Ptolemy tells us that there's an error because Hipparchus had some parameters of the moon incorrect, and Ptolemy says that better methods were available in his time. So, he proposes to use them. Ptolemy again searches through the ancient records to find a pair of eclipses, but this time with very specific properties. What he was looking for were eclipses that were very similar in nature, being not quite total, but obscured by the same amount on the same side for the same amount of time, and while the moon was roughly at the same distance from the Earth. He imposes these criteria because it means that the moon must have been at approximately the same ecliptic latitude for each eclipse, which we can tell because the same amount of the moon was outside of the umbral shadow, which has a pretty consistent diameter. Lastly, he required that these eclipses both happen near the same node. Finding a pair of eclipses that suits these requirements, he's able to geometrically work out how far the moon moved about its epicycle in that time by using the mean motion tables. And he notes that the moon wasn't in the same position about the epicycle at each of those times. This indicates that the moon hadn't completed a full cycle in longitude, which should also be expected for the pair of eclipses since Ptolemy specified that they both occur near the same node. In other words, Ptolemy has demonstrated that the moon returned to the same ecliptic latitude faster than should have been expected. And knowing this, he's able to work up a minor correction which he uses for the values in the mean motion tables. And with that improved value, we can then determine the position of the moon in ecliptic latitude at the start of the epoch, if we know the lunar latitude at a specific point in time that we can rewind from. You might be tempted to think that we could use basically any of the eclipses that we've just been talking about. Since for eclipses to occur, the moon must be close to the ecliptic. But it need not be as close as you might expect. Again, the Earth's shadow is 2.5 times the width of the full moon. This means that the moon could have been a fair distance above or below the ecliptic, and you'd still have a total eclipse. Thus, we don't know its true location. However, the further it is from the ecliptic, the shorter the eclipse's duration. So Ptolemy could have done pretty well just by choosing the total eclipse with the longest duration, and been pretty sure it was very close to the ecliptic. But instead, he chooses to do something more complicated. He again finds a pair of eclipses with some specific requirements. This time, he wants ones which have the mean positions of the moon roughly the same distance from opposite nodes. Using some geometry, he is able to determine how far the moon's mean position was from the northern point, the point at which the moon has its greatest latitude, for one of the eclipses. Then it's a simple matter of rewinding the moon from that position by the amount of time between that eclipse and the epoch. Doing so, he finds that the moon's mean position was 354 degrees and 15 minutes from the northern point at the start of the epoch. Having concluded this, Ptolemy then tells us that we're ready to create our table of anomaly, which will tell us how far ahead of, or behind, the mean point that the moon is thanks to its epicycle, based on how far around the epicycle it is from apogee. This is then laid out in Chapter 10, wherein the first two columns are the distance of the moon about the epicycle, and the third is the amount of anomaly. If the moon is 0 to 180 degrees from apogee in the first column, then the anomaly should be subtracted from the mean position, and if 180 to 360 degrees, it gets added. That basically completes the lunar model for now. However, Ptolemy puts in one more chapter, which strikes me as more of a historical footnote than really part of the model itself. Specifically, he notes that Hipparchus evidently had two values for the maximum lunar anomaly. In one case, he states that it was 5 degrees and 49 minutes, whereas in another, he gives it at 4 degrees and 34 minutes. So how did he arrive at two different numbers for the same value? Ptolemy states that this is because Hipparchus derived lunar models using both the eccentric hypothesis and the epicyclic one separately, resulting in a different maximum anomaly for each. This should surprise you, since we previously stated that the eccentric and epicyclic models should produce the same results. But that was only true if certain ratios related to the eccentricity were kept consistent between the two models. Ptolemy reviews how Hipparchus worked out the values and finds that Hipparchus did not have those ratios the same, which explains the discrepancy. But why didn't Hipparchus keep those ratios the same? Ptolemy attributes it to an error in the math in which Hipparchus incorrectly determined the length of time between two of his eclipses. Ptolemy then recalculates the base parameters for the eclipses, demonstrating where Hipparchus's errors likely were, although he stops short of recalculating the eccentricity specifically. I found the choice to stop the calculations there a bit of an interesting one, as without doing so, he doesn't demonstrate that he can truly reproduce Hipparchus's values. Regardless, that digression closes out Book 4. At this point, we have a working lunar model which allows us to calculate the lunar position at any time. This model is almost certainly similar to the one that Hipparchus created, at least in how it's constructed with the moon on a simple epicycle, although, as we've seen, Ptolemy reviewed and tweaked specific parameters. But Ptolemy has also told us that it's fundamentally flawed and doesn't produce accurate results near first and third quarter. So, in Book 5, Ptolemy is going to add a new feature to the model to help account for this. But we'll save that for next time, as we continue to explore astronomy before the telescope. Hi everyone, this is my adorable cat. Her name is Riri, and she's being very naughty right now, not letting me record a video because she wants to play the runaround game. So we're gonna go take her and deposit her with Mommy.